We have a special format. For the first time, we try to have a conversation. I give you an introduction, and then we have a conversation with two PhD students here, which focus on this topic of urban measurements. So let's start with this one. So it's myself, it's Estefania Tapias, who you already know quite well, and also Daniel Gregor, who will discuss on measurements here for a while, and we hope that also you then get involved and ask questions. I will ask them questions, and maybe by doing this you get a better idea what it is about. Does it not connected? Is it? So we are, thank you. We are here now on our fifth lecture. It's on the conversation on measurements in the city. And this is, of course, in context with the next lecture, which will be on urban science. So urban research and urban science are closely related. The story so far, the last time, 2 weeks ago, if you remember, we had this big topic of stocks and flows, why they are important. And from this rock falling down, you could visually see how a stock, a mountain stock, is turning into a flow. So this is just one link. But we could see that stocks and flows are fundamental concepts for understanding the working of a city and also of a smart city. And today it will be the metrics of the smart cities as basic instruments of urban research. So urban research, what is this? We have many thoughts about this, and you can have all kinds of research, but urban research is something really special. It's also relatively new compared to other researches because cities as big entities are relatively new if you look at the history of mankind. If you remember this image here, this obviously is a result of urban research. That is the traffic simulation. And if you remember what simulation is, simulation needs an underlying model. It needs to have connections between the parts of the model, and then you can project something into the future that you want to have as closely as possible to the real thing. In this case, the real thing would be the movement of cars and other vehicles in a city. So this is the result of urban research. But today we want to go a bit deeper and look how we actually do that. And for that, we have to try to understand cities. The understanding of cities is a big topic that will probably never end, but I want to give you some, or exactly one, route of understanding cities that is quite known to maybe some of you, but it's at an early stage of urban research. We had a person, a mathematician actually, whose name was Christopher Alexander. Does any one of you know Christopher Alexander? Ever heard of him? Yes? What did you hear of him so far?
The notes on the synthesis of form.
The notes on the synthesis of form, exactly. And he also wrote the pattern language. And he also wrote another one which is quite famous, another book in the 60s, in the middle 60s was already. That's called The City is Not a Tree. And The City is Not a Tree, this is an excerpt from this book. And I think it's quite helpful to understand how different people view cities and try to understand cities. So he writes, "The tree of my title is not a green tree with leaves. It is the name of an abstract structure. I shall contrast it with another more complex abstract structure called a semi-lattice. In order to relate these abstract structures to the nature of the city, I must first make a simple distinction." And here, of course, already people from today get very uncomfortable sometimes, but he made it very simple. He said, I want to call those cities which have arisen more or less spontaneously over many, many years natural cities. And I shall call those cities and parts of cities which have been deliberately created by designers and planners artificial cities. So the persons who have been, for example, to China, they maybe can follow this distinction quite clearly, because in big countries like China or India or United States, you have both of those. And he makes the examples: Siena, Liverpool, Kyoto, Manhattan are examples of natural cities, and Leviton, Chandigarh, and the British New Towns are examples of artificial cities. At this time, in 1965, all this huge, fast development in Jakarta or in Asia had not happened yet. It's more and more widely recognized today that there is some essential ingredient missing from artificial cities. When compared with ancient cities that have acquired the patina of life, our modern attempts to create cities artificially are, from a human point of view, entirely unsuccessful. Both the tree as an abstract structure and the lattice, the semi-lattice, are ways of thinking about how a large collection of many small systems goes to make up a large and complex system. More generally, they are both names for structures of sets. Those of you who have studied mathematics, of course, in high school and later, they know what this means. But an interesting point here already in 1965, he's talking about complex systems. So cities belonging of, or being comprised of different parts, smaller parts which work together to form a large and complex system. And I don't want to go deeply into it, but come to the end. He also graphically shows this. He makes a comparison between a so-called traditional communication and traditional communication within a group of friends in a village, say. And in a traditional society, if we ask a man to name his best friends and then ask each of these in turn to name their best friends, they will all name each other so that they form a close group. A village is made up of a number of separate close groups of this kind. That was his idea, that the new city should be comprised of villages that are more or less close group that can very seamlessly communicate with each other. And then he says, but today's social structures are utterly different. If we ask a man to name his friends and then ask them in turn to name their friends, they will all name different people, very likely unknown to the first person. These people would again name others and so on onwards. There are virtually no close groups of people in modern society. The reality of today's social structure is thick with overlap. The systems of friends and acquaintances form a semi-lattice, not a tree. So this is what he said is a tree, traditional, and this is the semi-lattice, which is modern at this time, 1965. And if you look at this and compare this to the representation of the internet, for example, or social media, you can immediately see what he was pointing at or what he was already understanding. So therefore, he was pretty far ahead of his time. And today it sounds very simple, maybe simplistic, but it showed that he had thought into the right direction. So if we think of the model of a city, understanding a city, this is an important reference. Now, let's go into the metrics of the smart city. And this is where these strange images are coming, which you might first not directly connect to the metrics of the city. But there's a very simple saying that, you know, from many different sources probably, it's attributed to all kinds of people. This one here is from the mayor of New York, the former mayor of New York, Michael Bloomberg, who said, I have a rule of thumb, if you can't measure it, you can't manage it. That's his idea. And therefore, you have to measure it in order to manage it. And other people, other sections of this, or other variations of this saying are, if you cannot measure it, you cannot improve it. Which is probably not true, but it sounds pretty simple. So let's start from this quote anyway, and look at some of these events here. What happened here? Do you see what happened? Yes, can you see what happened?
Yes.
Okay, what do you think happened?
He didn't measure correct, huh?
The driver.
Measuring alone is not enough. shows. I mean, it's very tragic. Nobody was killed, fortunately, but many people were injured. And so this is an underpass close to Lille in France. And the poor gentleman driving the bus, he missed something quite important. So when we try to develop towards smart urban systems, we always have these interactions between urban stock and urban flow. Remember last lecture. Here the urban stock is the tunnel ceiling, unfortunately. It's really a stock. There is no flow in this. But the urban flow, the transportation, that was the moving part. This was the bus. And if you want to understand what happened, you see here what I highlighted. These are the things that worked. And what which is not highlighted, it didn't work. So can you see it from back there? Yeah? Mm-hmm. Yeah? You cannot see it from the side. Okay, so there is a model, because obviously this tunnel had a 3D model, and it was also measured, so everybody knows how high this was. And this model, there was a street in the model, because the bus driver was driving with a GPS. What he did not do was the checking if his bus would fit into this tunnel, although there were signs. But for some reason he was confused and he just drove in anyway. And he didn't understand, or there was no understanding of what would happen. There was no warning. The GPS didn't warn him. Any other thing didn't warn him. And there was no action that he would stop the bus. So this was not a smart part of a city, obviously. This one here, this was this rock that I showed in the beginning, is quite the opposite. Because in this rock, it's not a city, but you can make the analogy to the city. What they already knew from this rock, it is a comparison between alpine stock, the rock, converting into an alpine flow, which is the rock avalanche. And what happened in this case was quite obvious, because they had a model, let's say, of the Alps, of the 3D geometry of this rock. They had a model that temperature change would probably do something to the Alps, to the movement of the rocks. And because they knew that and anticipated that, they did measurings. They did measurings on this rock for quite a while. So they were seeing that the measurements were accelerating. They did the checking every day automatically. And once they saw that the the measures of movement of this rock became bigger, they started to understand, this rock is going to come. And not only did they measure it, they also understood what would happen. Then they put the camera there. Then, of course, they did the warning. They warned the people around there that nobody should be in the vicinity. And then the action was that that thing actually fell. So here, this was a complete predictive, step-by-step procedure, if you want, of a smart system. Now, this is just a rock, say just a rock in the field, but this might happen almost anywhere. And my point I want to make with this, it is very important that you have a model of a city, that you are able to measure, that you can check it, that you understand it, that you have to give warnings if something happens, and that there has to be some action, escaping or doing something other meaningful. Otherwise, it will be deadly. Speaking of deadly, this is really unfortunately true. This image here, this is, I think, a very shocking image. Some of you might know it. This is from Pompeii. And these are the actual people, the actual bodies of persons, not the bodies themselves, but the hollow frames of the persons in the ashes that then were filled with gypsum, with plaster, and could be shown. So it's like a mold of these people, which were found exactly like this. So they were killed. But if you think, why were they killed? They were living in the city, and it was in 69 or 73 after Christ. And they were living in front of this mountain, this Vesuvius mountain. They had built this wonderful city. they had some warning signs because like 10, 12 years before the eruption, there was earthquakes, and they even knew that there were earthquakes. They kept the record of it because they had depicted drawings or mosaics with the tilted columns after the first earthquake, yet they didn't do much about it. There was a highly sophisticated society. Now later, when we talk about measurements of buildings, we will see that this was really sophisticated. These were the Roman hypocausten heating system. It's like a double floor. You had the heating from underneath, not only the floors, but even the walls. Here, you can see it on the side. Even the walls were heated. So it was not a simple society. It was very sophisticated. And also they had all kinds of art. They even look at this, the perspective they already had, which was only rediscovered many, many hundreds of years later. So how could it happen that they didn't check it? So what happened? They didn't have a model what this meant. Although after the first rumblings of the mountain, their water supply, which was also sophisticated, already coming in leaden pipes almost 2,000 years ago, stopped running. And they didn't have a model. They didn't know what to do. They didn't do the measuring. They did some checking, some visual checking, because he saw this mountain erupt. But even after they were covered with ashes, after the first evening, they didn't take the right decision. They didn't understand it. They didn't take this warning sign. They didn't take action. They just remained there. They waited. They thought it's over, like a thunderstorm. And then, of course, what happened? The next day, the whole plume collapsed, and then you had this terrible hot air and hot ashes and hot lava coming down and wiping out everything and everybody. So the point is this: in a smart system of a city, it is very important to have all these things working. Today, hopefully, that would never happen again, because in many, many places in the world where volcanoes are active, all these chain of actions have to be taken, and mostly are taken. Okay, so let's go to a less deadly example, and let's go to this conversation of measurements in the city. And for that, I want to introduce two case studies, and I want to ask Danielle and then Estefania to introduce their case study. We're moving from the city now to a building. And Danielle, go ahead.
And I'll also take this. So today I'll speak a little bit about measurements in the city, and or I'll speak more about measurements in buildings, and then Estefania will talk about in an urban environment. So sort of outdoor measurements, I'll speak more about indoor measurements. So the first thing that I want to kind of, I also highlighted as well as we discussed our slides, if you cannot improve what you can't measure. That was sort of the philosophy which I had for the majority of my academic and professional career. So what type of data do you need? And then what can you do with that data? So I'm going to present a few case studies which I have worked on. Let's see. I'll just put it all together because the animation didn't work out as I wanted. But I'll start over here with typical measurement devices in a building. So we're all relatively familiar with thermostats, light switches, and this is a control device which senses if the window is open or closed. So these are relatively common elements, sensors in a building. You could also have energy meters. They're kind of ubiquitous in a building. And so typically it's isolated in this system right here. So you send this information to the building management system. It regulates if you turn on or off your heating system or your cooling system for that particular space. So it provides the standard indoor thermal comfort for your space. So it sort of typically exists in this environment. But most people might consider that a smart building. because you have some method of controlling indoor temperature and requirements. I don't believe that actually this isn't smart. It's because you can't actually do anything with this data. So you can't look at your data afterwards. So as Professor Schmidt mentioned, you want to be able to look at this data to make better predictions in the future. So the next step typically is to provide some sort of database. Okay, we can store that data. But that's often what happens in buildings. It just sits there. So what the next step really to make a building more intelligent is to have some method of visualization, benchmarking, prediction, and then what I think is an intelligent building or a smart building is when you have a control method that takes this data in real time, which is typically a demand control system. It makes modification to the building management system, and then it updates the thermal comfort quality in the space. So for these types of smart systems, the operational energy consumption this is in the US, is anticipated to save about 22% energy for all building stocks if implemented correctly, which is very possible. And close to $50 billion of operational costs are also saved. So this is something which, you have a question?
As it's a conversation,
Sure.
maybe you can just recall what you saw before. And also, you should say, these things, they're actually here in this building, right?
Yes.
Yeah,
Yes.
you can actually look at them. That's why I chose this example. You can actually look at them. You find those sensors all over the place. And if you relate it to what you saw before, either in Pompeii or also this rock coming. So if you just have this, it's not so smart. But if you have the visualization and, most important, the prediction, then that way they could predict the rock is going to come. And it was a smart setup in this case. So from a smart building to a smart city is a relatively small step. Go ahead.
And so this is, again, my animations didn't happen to work out as I wanted, but I could just walk through them sequentially here. So this is a project that I worked on while I was at the Energy Research Institute at NTU in Singapore for 2.5 years. And one of the first tasks that I was given was to benchmark the campus buildings at NTU. So benchmarking, okay, what does this mean? It means classifying your buildings. And so I was working with mostly laboratory facilities. And laboratory facilities have a wide variety of energy demand qualities, such as could be a chemistry facility, a physics laboratory, a math laboratory. So you have different demands for different building types. So there was a big research that went into develop laboratories for the 21st century. And so they consolidated large data sets, large databases to compare thousands of building laboratory facilities around the world, and so that they can come up with benchmarking metrics to compare laboratory facilities, because you're going to have very different energy demands for different laboratory facilities. And that changes per climate, per use type, so on and so forth. So they've kind of created a really robust database so that you can have start to compare yourself to your peer groups. So this is where this came from. And I did that for the laboratory facilities at the NTU campus. So this really was insightful for us because this had never been done. And so they had 8 major laboratory facilities on the campus. One in particular this is their highest energy consuming facility. So this is kWh per meter square per year. And it also had roughly the same amount lab area ratio, which is around 40%. That was pretty standard. So even with this one, having close to 60% lab area ratio, it was not necessarily the highest consuming laboratory facility on the campus. So this is information that gave us. We worked on energy efficiency for the campus. So we looked to say, okay, we really need to address energy issues and energy conservation for this particular building. They hadn't done this so rigorously before. So then taking that a step further, we looked at the floor area ratio for this particular building. So the majority of it was chemistry laboratories. Then there's also physics, maths, and then other types of sort of fractional lab space.
So you say this was an insight for you, and that also means that if you had not measured this, you wouldn't have seen it, right?
Precisely.
Nobody would have known. Yeah, okay, so that was a new finding from this study.
Yes, and so, as I said, this data had been sitting in that database for years. So they had collected this data, but they never actually did anything with it. So this was something which was, you can't really gain any insights if you don't run any very simple analysis, but you can start to reveal interesting things from that. So yes, my animation actually worked. So, so this was something where we looked at the whole research facility, and then you can go into more system level analysis. So first, looking at this research facility, you can do very high level metering and you can get information, as I showed before, the energy consumption per square meter per year, and then the lab area ratio. See, these are very high level analysis that you can do.
But it's just trees. And what we showed before, city is not a tree. This is just expressed as a tree. This is a representation of a tree-like structure.
Yep.
So you break down the building into pieces, but you don't have any interaction between the pieces yet in this representation.
Yep, not yet.
Not yet. Okay,
Yes.
so.
Exactly. And so the next level, so that these measurements are from whole building, as I'm saying, to system level. So the next step is to get more disaggregated energy consumption measurements. So what you're consuming for your chilled water, ventilation, lighting, and your receptacles. So anything is your plug loads. So these are also for the different these different lab types. So then, as I said, we focus on chemistry. One particular lab wing, which was representative. This is representative of 3 different stories. So the majority of the building floor area in that lab wing, in the chem lab wing. So then from the lab wing, we went down further and we had measurements. I'll show in the next diagram on the next page. We had some measurements that were already existing in the building management system, some which weren't, and where we needed to add more sensors and meters to collect that additional data to have a more holistic set of information. So this was as I said, some of this system was already measured, some of it wasn't, but all of it was just sitting in a database, and it was used to control the system. So it was doing its job. And like its very basic requirements for supplying the right air quality and the right temperature requirements for those laboratory facilities. So it was doing its basic job. But we thought, okay, we have this issue of a really high energy consuming facility. We need to reduce it. So one particular issue for these lab spaces are the dense fume hoods that they have. So if you've ever been to a laboratory facility, these fume hoods consume a lot of energy because they're conditioning this high volume of air in Singapore. This is the highest quality of air that you can supply to a space. It goes in and it goes right back out. So it's supplied to the space and immediately sucked out and sent outside to these exhaust plumes. So you're conditioning these huge volumes of air that is then just exhausted right out. So that is an issue when you're looking at energy consumption. So this is when we decided we're going to make an energy dashboard for this, for the people who are in this space. So all of these researchers that are in there, they can see the impact that it makes when they leave their fume hood sash open. So this was used as an initial test case for them to see that yes, your energy consumption is actually going to be increased substantially in your space, and you are contributing to this negative or to this energy consumption in your space. But they could actually start to see it, and we were working with the professor for this lab, and he was thrilled that he can finally measure this and say, because he was always going around saying, hey, close your fume hoods, but nobody had this real incentive to actually do it. So now he had a visual method to say, hey, you left your fume hood open last night, and that, so he could sort of use this in real time, which was a great outcome. So,
2 more minutes.
oh,
yes.
have nothing. Okay, I have a lot more to share, but I'll just continue with this one. So for the rest of the spaces that weren't fume hood driven, we actually were working with a company to install this sensor suite, which they were looking at other metrics, but you want to use this type of sensor suite to control spaces that were not actually human operated, so fume hood driven. So this was the communication network that we set up for it, which was really cool because we did it for one building space, and then the campus was interested to expand it throughout the campus. And then on top of that, we had a set of analytics that we wanted to run. So this communication network is kind of representative of what I showed in the previous slide. And then these are all of the data that you would need to go into this system, collect it. You have a data warehouse, and then you have different types of analysis, and then you always have to have a visualization platform for different types of use. So you can have a use for the public, you could have the use for the facilities management, you could have use for the occupants. So you just sort of, you tailor it to your audience. So I can go over this briefly, but I'm now working at the Hunkerberg campus with a similar set of analysis that I did at the previous, in my previous work. So right now I'm just looking at the floor area ratio, similarly to what I did at NTU. So what I wanted to highlight in this particular example is the historic data analysis. So when we ask in the assignments, what type of data is it? It's historic. It happens, it's more static data. And then there's real-time data. So this is time series data analysis that you can make, which you look at what's occurring at any instant in time. But again, at this point in time, it's just a set where you can have fault detection analysis and other types of analysis. Shall I just skip through this?
Yes.
Okay.
Yes.
And then this is the only thing I want to say about this. It's spatial temporal data. So that's another way that you can display large data sets. And my final conclusion, I think we've said it several times, but pretty much all buildings and campuses have meters and sensors. But for building purposes and building systems control, but it's not necessarily smart. Unless you run analysis and specific control systems on it. So, with that, I'll...
Thank you. Thank you. And now comes and keep in mind those different ways of looking at historic data. This is for learning from the past. And then she went to real-time data, learning from now for the immediate future. And that's where we start with Estefania.
So now going from Singapore all over to another part of the world, which is still the tropics. We are doing now research in the Caribbean, in Barranquilla, Colombia. And in this research, we also have the same idea that we want to collect data. In this case, it's outdoor, a difference from the other example. So we collect weather data, outdoor weather data, and then with that, we want to do a series of analysis based on outdoor thermal comfort, and at the end try to get some findings of the relationships between the urban geometry and the collected weather data. And then for this, what we did is that we developed a method where we first had the data collection, so we design a measurement system outside a campus of the university. And then we started collecting the data since last year, October last year, so it will be already 1 year. Then we also, at the same time, we had a software that was processing the data meanwhile. And then after that, we wanted to do some thermal comfort calculations with the data we got. And then afterwards, we wanted to create a simulation of the city according to the data that we collected before. Right now I'm just going to show you the first part, the collection of the data and the measurement campaign we did, the measurement network we designed. So what we did is that we put several weather stations around the campus of the university with different orientations and with different types of weather collections. We connected it to a computer, a Raspberry Pi computer, which is shown in this side. We connected it to the weather station, and then at the same time the computer was connected to a web server. And then during the meantime, during all this year, we could monitor all the data collected by the weather stations. So that was the system that we designed, so we could monitor the weather, the data collection from the weather stations, and at the same time, the software from the weather file, it also gave different analysis. So it started doing data processing meanwhile, so we could have the mean values for the day, for a month, and even for 6 months. This is the setup of the measurement network that we did. This is one of the weather stations. And this is how we monitor and how we see the monthly statistics of different weather parameters like temperature, rainfall, solar radiation, etc. And also the mean values, as I mentioned before. But of course, it's not only about collecting the data, but as we already mentioned, the idea of collecting this data is that we can analyze the data. So it doesn't get stored, as Danielle showed before, that it stays stored for a long time, but that we can grab the data and we can analyze it. For this, we want to do some analysis of the thermal comfort, of the outdoor thermal comfort, and we already got some insights, we already got some results of the weather comfort. But what I wanted to highlight today in this course is that for a smart city or for a smart system is not only about the data that we collect according to sensors or according to the different technology that we have, but we also have to get the data from the people. So I will think, or my opinion is that a smart system is not only about technology and sensors, but it's also what we get from the people. So for this, what we did also was Android application where we also get the insights from the people. So we analyze the thermal comfort with our models, with our computational models, but we also wanted to ask the people how were they feeling. So we only not get the data from our sensors and our technology, but we also get the insights from the people. I think right now, if you understand or if you speak Spanish, you can read it, but it's not in English, unfortunately. But what we mainly ask here is how they feel, if they feel cold, if they're comfortable, if they feel warm, where were they before, if they were in an indoor, or if they stay a long time in the outdoor space. And the idea with this is to gather both database, so the data we get from the people and the data we get from the weather stations, and start doing some analysis and some correlations for what the final goal will be to learn from the thermal comfort of people in the city and have some insights of how the city should develop in the future, or how we should develop the open spaces for pedestrians to feel more comfortable with the weather. So this was my input.
Thank you very much. So you can see these two women, they're actually not talking about the smart cities only, but they're really doing it. And again, these different aspects, the long-term data, the historical data, coming to the real-time data, coming to the real-time data that you are doing, these measurements, which are really readable as we are speaking. She can open up those tables and can look exactly what is happening right now, is very important. And one thing you have, so you said the data is not stored very long, but we want to analyze it. Of course, by analyzing data, you don't destroy them. They're still stored, but they are being made more useful in this case. Okay. So that leads us to the exercise. Your exercise that you're doing now. You can go back to the other. Yeah. Yeah. Just for the exercise that you're doing right now, I hope you all downloaded this one, and you got it from Danielle directly, and you're working on it now. And I think it's important that you come to the base or to the essential parts of this exercise. So that is an example from last year's exercise, which was on livability, just to show you that it doesn't have to be highly sophisticated drawings, but that sketches are really enough. Can you just maybe move? Or I can help here. So this person worked with tables to explain what he's trying to say. He worked with maps, simple maps. He put in arrows and some expressions, and he worked with simple sketches, which are very clear. So even those of you who study physics or mathematics, I think everybody can do these sketches. That's enough. This is enough to express what you really want to show. Okay? So don't worry about this. Here you can clearly see it's a street. You want to show what the buses are doing, what the pedestrians are doing or not doing, what they should do. So this is important that you come to this level of explanation what you mean. This is what we want to get out. What you mean. Not totally perfect. Maybe we can come to the conclusions now. The conclusions from today are simple. As I think, all could see that urban research requires measurements resulting in data. But only if these data are combined, they turn into information. These tables alone don't tell you anything. And if information is combined, it turns into knowledge. So this is what you can see from this book that you're reading for your second exercise also. Information and knowledge combined with observation and compliance are needed to improve a city. That holds for a building, it holds for a campus, as Danielle was showing. It also holds for a whole neighborhood, a whole city, as Danielle was showing. To understand urban systems, measurements are important on all scales. Buildings and neighborhoods, that's what we saw. Districts and cities, you can do the same thing on the city level, and regions and territories. Measurements are necessary, but not sufficient activity for quantitative and qualitative urban improvements. And the last point, that what you saw the examples from the beginning, is that ignoring information and knowledge or not having access to it can be really deadly in any normal activity like transportation or big-scale territorial activities like volcanoes or tsunamis. So with that, hopefully, point for measurements and their meaning, I want to leave you and come back to your nodding head that measurements are not the only way to improve something. Something can be improved sometimes even without measurements, but that's something for you to think about more deeply. So with that, I want to leave you. Have a wonderful afternoon, and see you next week. I'll be here to answer questions afterwards. Thank you.